Education Award and 2017 Wine Best Paper Award. From 2013 to 2017, he was the editor-in-chief of the IEEE ASEAN Transactions on Networking. With this, let's welcome Professor Srikant. Thank you.
Thank you, Arkadeep, for the kind introduction. Can everybody hear me?
Yes, we can hear you.
Okay, good. Yeah, and thank you all for being here on a Sunday morning to listen to this talk. So I'll be talking about performance bounds for policy-based average reward reinforcement learning algorithms. And this is joint work with Yashashwini Murthy, who's a PhD student here, and Meherdad Moharami, who's a postdoc here. I think most of you know about reinforcement learning probably, or at least it's been in the news a lot. And just to give you some idea or high-level motivation for reinforcement learning, I worked with a car company to design a lane merging algorithm for their electric car. And roughly speaking, this is how it works. So you have a reinforcement learning agent, which controls the movement of the car, and it takes an action. So the action could be to drive, to accelerate, decelerate, brake, maybe move to the left lane, move to the right lane. So one of these things could be an action of the car. And the action of the car changes the state of the system around it. So the state of the system in the context of autonomous driving vehicles or electric vehicles is the relative positions of the other cars and other vehicles on the road. So for example, you may have 10 cars around you, each one is going at a certain speed, and one of you is a certain number of meters away from you and so on. But because you're accelerating or changing lanes, of course, you're changing the state of the environment around you. So you take an action, it affects the state around you, and you observe this effect that you had. Let me get a pointer out. So you can observe the effect of your action. So you get to observe the state. So you have cameras and other kinds of sensors in electric cars that record what's going on around you. So therefore, you get to observe the state of the system. And you receive a reward for each action that you take in a particular state. For example, in this autonomous driving situation, you might get a negative reward or a cost for getting too close to another car, and you might get a positive reward for driving faster. Okay, and you might get another reward for if you're for example in the application that I mentioned, if you're entering a highway, then you might if you're able to merge onto the highway from another road on the side, then you would get a higher reward. So you take an action, you change the state of the system around you, you observe the changes that you made, you also get to observe the reward, and then based on this, you take an action again. So this is a standard control system. You have a state, you have an action or a control action, and that gives you a reward or a cost associated with that action. And reinforcement learning tries to learn how to take optimal actions. So since this is a communication network conference, another type of example, or communications conference, another type of example is what happens in communication network. So I don't have a picture for that here, but basically you have very large data centers, and in data centers you have to schedule jobs. Traditionally, we would do simple things like when a job arrives, you try to route it to the queue that has the smallest number of other waiting jobs. So like when you go to a grocery store, if there are multiple lanes for you to join, you would join the lane with the smallest number of customers ahead of you. But that's for simple jobs, but modern jobs are very complicated. A single job consists of many tasks, and there is an order in which these tasks have to be executed. And in such situations, it's difficult to figure out what the optimal thing to do. So there's no analytical expression for this. So there's been a lot of interesting papers that have come out in the last few years trying to figure out how to allocate resources in a communication network. Another example is wireless network, something that Argadeep, for example, has worked on, which is like in the context of assigning frequencies to radios. Again, you can set this up as a Markov decision process, and then you can use reinforcement learning to solve the problems. Reinforcement learning has had great successes. The most popular ones that you read in the literature are in the context of playing games such as AlphaGo, AlphaZero, Atari, and so on. And in the context of practical applications, for example, robotics. And there have also been a lot of successes in the context of communication networks, as I mentioned, in the context of wireless networks, in the context of data centers, and so on. They don't make the news as much as these game playing applications do. But clearly, it's an area that's emerging, and more applications are expected as we progress in time. So for the purposes of this talk, what I'm going to assume is that underneath this system for which you're going to design a reinforcement learning algorithm, there is a dynamical system. The system that we have can be described by a dynamical system. So here, X is the state of the system. U is the control action that you take, and there is randomness in the system that I'm just calling WT. So the new state at time t+1 is, of course, a function of the current state and the current control action, and there is some randomness that you cannot control. So for example, in the context of autonomous driving vehicles or electric cars, the positions of the other cars are something that you cannot control, or there is noise in the cameras or the LiDARs, the radars, or whatever you use to measure the state of the system. So there's noise in the system that's inherent. In the context of the communications or communication networks, so X could be the vector of queue lengths, and the U could be the action, basically routing a particular task to a particular queue will change the contents of the queue. And then, of course, because we don't know how long it'll take to process a job or what is the statistics of the arrival process, so there is randomness in the problem. So the most common performance criterion that's used in the literature is the discounted reward problem. So at each time instant, you get a reward R, which is a function of the current state and the current action. And you add this reward, multiply this reward by a discount factor raised to the power of t. So the idea here is that future rewards are less useful to you than current rewards. And you try to, this is the objective. So for a fixed policy, for some fixed way to choose u as a function of the state, this is what's called the value function, which is the function of current state where you start from, okay? And the goal is to, if you look at most of the reinforcement learning literature, the goal is to maximize this discounted cost. For the purpose of this talk, I'm going to further simplify what I said in the previous page. I'm going to assume that we're dealing with finite state spaces and finite action spaces. So if I'm dealing with finite state and action spaces, then the dynamical system can, of course, be expressed in terms of a probability transition. So you have a probability of transitioning to state J, starting from state I, when a control action U is applied. And so, as I mentioned earlier, so if you fix a policy mu, then I'll use typically I to denote the current state. So V mu of I is what's called the value function associated with state I for a fixed policy mu, where mu basically is a mapping from states to actions. So these could be randomized, these could be deterministic, and for whatever it be, so you have a value function associated with the current policy. So it's well known that the value function associated with the fixed policy satisfies a simple recursion, simple fixed point equation. So the value function associated with the state I is simply the immediate reward that you get at state I by taking action U, which is mu of I, plus alpha times the future reward that you get. So this is, of course, very meaningful. And for any of you who've taken a class on MDP, this would be one of the first things that you learn in such a class. And of course, to find the optimal action in each state, what you do is the right-hand side here is a function of U. So you just maximize over U to get a fixed point equation for the optimal value function. So this is called the dynamic programming equation or the Bellman equation. So in terms of operators, so this is often written in terms of an operator. So here, the value function at each state I is a function of all the value functions at all the other states in the system. So it makes more sense to write this in vector form. So if I call v mu as the vector associated with is the value function vector, then this whole thing can be written as v mu is some function of v mu itself. So this is called a fixed point equation. And similarly, the optimal v is also a function of itself, and this operator we call t. So the nice thing in the discounted cost formulations is that both T mu and T happen to be contraction mappings. So the fixed point happens to be unique, and this property can be used in many, many ways to define many, many algorithms. And what do I mean by contraction mapping? So if you give V as input and V tilde as another input, so T mu V minus T mu V tilde, the distance between that is less than or equal to some alpha times V minus V tilde. Since the discount factor alpha is a number between 0 and 1, if it is strictly less than 1, we have a contraction of the distances, right? So this is called a contraction mapping. Again, I am probably boring many of you because this is something that most of you probably know, but I just wanted to make sure that for a general audience that everybody's on the same page. Okay, so the basic algorithm, one of the basic algorithms that is used to compute the optimal policy works as follows. The reason I'm starting with policy iteration is that the large class of reinforcement learning algorithms can be thought of as some variant of policy or some approximation to policy iteration. So what you do in policy iteration is you fix a policy, you compute the value function associated with the policy by solving this fixed point equation. And then you obtain a new policy by pretending that this v mu is the optimal value function and sticking it on the right-hand side of the Bellman equation, you get a new policy. So this is called the policy evaluation step, and this is called the policy improvement step. You repeatedly apply these two, and then it can be easily shown from a first class in MDPs that you have convergence. The policy improves at each step, and since you have a finite number of policies, eventually it'll converge. So in terms of the notation that I introduced earlier, the policy improvement can be written as T of V mu is T mu of V mu. So anyway, it doesn't matter what the notation is too much, but that's for those of you who are interested in it. But why can't we implement policy iteration in practice? So there are two reasons. One is the probability transition matrix may be unknown. So if the probability transition matrix is unknown, you cannot implement either of these steps, right? Because the first step requires you to use the operator T mu, which involves a probability transition matrix. The second step involves improving the policy, which also needs a probability transition matrix. So you can't do that. But let's say you are even given the probability transition matrix. So for example, in games like chess, there is no probability involved, right? So you're just playing with an opponent. So if you pick a move and move a chess piece, clearly, there's nothing random about it. So everything is deterministic. Of course, the opponent picks a move. There's a game aspect to it, but ignoring the game aspect to it, the transitions are purely deterministic. But the problem is, there's in theory, chess can be solved as a dynamic program, but you cannot do it because Shannon computed the number of possible chess positions to be 10 raised to the power of 120. So this is called the Shannon number for chess. So the number of states is simply too large. So this kind of a computation cannot be done. So you cannot find out what the optimal policy is in each state, for example, and store it. It's just impossible to do that. So you have to make approximations, right? So I'll skip that slide and then I'll go to this slide. So many reinforcement learning algorithms can be thought of as implementations of approximate policy iteration. What is approximate policy iteration? So at step K, let's say you have a policy mu K. Then instead of evaluating this the value function associated with this policy exactly, which I would call V mu K, you compute an approximation to that, which I'll call VK, such that VK minus V mu K in the infinity norm is less than or equal to delta. Similarly, in the policy improvement step, instead of finding a new policy that optimizes that solves the Bellman equation, you try to find a new policy that approximates the right-hand side of the Bellman equation in the following sense. There is an error of epsilon. So both policy evaluation and policy improvement are performed approximately in reinforcement learning. And there is a beautiful result by Bertsikis and Tsitsiklis in 1996. It's a very short proof. And what they show is that if you do this, if you do approximate policy iteration, the difference between the optimal value function, which I call V alpha star, and the value function that you get by doing approximate policy iteration, they differ by an amount equal to by an amount upper bounded by this. So let's interpret this a little bit. So what this is saying is that if the policy improvement and the policy evaluation errors are small, if epsilon and delta are both go to 0, then you basically get policy iteration back, and therefore the error goes to 0. If not, you're going to get an error that's of the order of epsilon and delta, which is a very nice result, which says that they make a small error in policy evaluation, a small error in policy improvement, the overall error that you get by running this algorithm for a long time will be proportional to those two errors. While that looks interesting, for today's talk, what I want you to focus on is this denominator. So the denominator has 1 minus alpha square, which becomes problematic, and I'll tell you why it becomes problematic. And if alpha gets close to 1, this bound starts becoming large. So even if epsilon and delta are small, 1 over 1 minus alpha square could be a very large number, and so this bound can be bad. But nevertheless, there's a nice paper by Chen and Magaluri in AI Stats 2022, where they show that a large class of policy-based algorithms in reinforcement learning can be analyzed as special cases of approximate policy iteration, which I've shown in this page. And you can sort of simplify many results that people obtain for policy-based optimization by sort of starting with this Bertsikis-Tsitsiklis result. And for each algorithm, you can find an appropriate epsilon and delta and sticking it in here to get your answer. Okay. How are we doing questions? Are we going to wait till the end, or should I pause for questions now? Or sorry.
Hello, am I audible? Hello.
So is the yeah? Can you hear? Yeah. Are we? Should we do questions at the end, or should I pause for questions in the middle?
Yeah, I think we can have the questions at the end.
Okay, great, thanks. Okay, so I hope the introduction to approximate policy iteration and connections to reinforcement learning was clear. So that's much of the literature focuses on this discounted cost, discounted reward optimization problem. But for those of us who work in the area of communication networks or communications more broadly, we know that many of the problems that we look at, average reward or average cost is more meaningful. So for example, I mean, historically, we've thought about delays in communication network. I mean, performance criteria in communication networks is in terms of average delay. So you want to try to minimize average delay, or you want to try to maximize average throughput, or you're trying to minimize average packet loss. So these are all long-term average criteria or steady state criteria. In the case where the system is ergodic, this turns out to be the same as steady state criteria. So it's more meaningful for many communication contexts to look at average reward criteria. So in the context of the notation that I introduced earlier, so you have a reward associated with the current state and the current action. You add up all the rewards for the first t time steps divided by t. That is the time average of the expected time average of the reward. And then you let t go to infinity, and this is the average reward that you're interested in. So as I mentioned, So if you make R here the number of packets waiting in the system, or negative of the number of packets waiting in the system, so this would be the you would be trying to minimize the expected backlog in your network. So we are more interested in typically average reward problems. And so it'd be interesting and nice to build a theory, RL theory, for average reward problems. And of course, I'm not saying that this has not been studied. This has been studied extensively. But my goal here is to sort of, like in this paper by Chen and Magaluri, to make a connection between approximate policy iteration for average reward problems and reinforcement learning problems, and see how to connect up the two, because I believe that the proofs and analysis of these algorithms would be very simple if we can cast everything in terms of this approximate policy iteration context. Okay, so one nice thing about the average reward about average reward and discounted reward problems is that they are actually very easily connected. So if you think about it, let me just go back to this page. It's in the discounted cost problem, you have an alpha power k here, and there's no 1 over t here. So if you let alpha go to 1, then this becomes just simply sum over k equal to t minus 1, and t can be thought of as alpha plus alpha t times in the limit as alpha goes to 1. So if you combine these two observations, it is very easy to show that the average reward for a fixed policy is nothing but 1 minus alpha times the value function associated with any state I in the limit as alpha goes to 1. And you get this answer independent of the initial state under some mild conditions. Of course, you can come up with counterexamples where this is not true, but for most problems of interest, this relationship between discounted cost problems and average cost problems holds. So you take the average cost, discounted cost reward, or a discounted reward problems long-term reward, multiply by 1 minus alpha, and let alpha go to 1, and then you recover the solution for the reward for the average reward problem. So let's use this intuition and look at this bound that I mentioned earlier for approximate policy iteration. That's from the Bertsikis and Tsitsiklis book from 1996. As I mentioned, this is a very nice bound because it says that as epsilon and delta go to 0, the error due to approximate policy iteration, the difference between the value function that you get using approximate policy iteration and the true value function, goes to 0. But there is this pesky 1 over alpha squared term in the denominator. So I told you just now in the previous page, if you multiply discounted reward value functions by 1 minus alpha, you should get the average reward. So what you should do, therefore, is multiply this whole expression by 1 minus alpha, and you hope that the difference between the left-hand side becomes small as epsilon and delta go to 0. But the problem here is that if you're looking at average reward problems, you have to let alpha go to 1. So therefore, if you let alpha go to 1, this whole thing blows up to infinity even after you multiply by 1 minus alpha. So it doesn't give you a useful result for average reward problems. So there's something missing here. So there is a sort of a gap between theory and practice. In practice, what people do is that they choose a very large alpha and use it to approximate average reward problems, and then you will see that the algorithm is slow, but then it'll eventually converge to the right answer if you have enough compute power. Okay. But this bound tells you that if you multiply by 1 minus alpha and let alpha go to infinity, the bound is not capturing the fact that alpha going to 1 works for the average reward problem. In particular, I just want to set alpha equal to 1 right from the beginning and not approximate it, and I just want to directly apply algorithms for average reward problems. And the question is, I cannot use this right-hand side as a motivation to get bounds for the average reward problem. So there could be 2 reasons. One is this bound is really loose, or it could be that approximate policy iteration does not work in the case of average reward problem. And the answer is the bound is really loose, and that's the main point of the talk. Otherwise, I wouldn't be giving this talk. So indeed, approximate policy iteration works, and you can recast some reinforcement learning problems in terms of approximate policy iteration, even in the case of average reward problems. But before we are able to analyze that, we have to do something about this bound. Okay? So that's the motivation for this talk. So just to briefly introduce the average reward optimality equation. The average reward optimality equation looks very similar to the discounted reward optimality equation with one small change. So the value function is equal to the reward plus the value function in the future multiplied by alpha in the case of discounted reward problems. If you set this alpha equal to 1, it turns out that this value function v is now no longer the value function, but it's something called the relative value function, and you have to compensate for it by adding a j star. So it doesn't really matter, but you could just, if you're not familiar with the average reward optimality equation, just take this to be the equation. It's very similar to the discounted reward problem, except that there is a j star on the left. But it's also well known that under reasonable conditions, a solution to the average reward optimality equation exists. So, and one can also do a policy iteration for average reward problems. You fix the policy, solve this fixed point equation to obtain both v and j, and then you find a new policy by doing policy improvement, and you can show that this also converges. So the convergence proof is a little bit more tricky than in the discounted reward case, but you can show that this also converges. But the same computational issues that we discussed for the discounted reward case applies here as well. So for one thing, you may not know the probability transition matrix. And also the size of the state space is so large that these computations cannot be implemented in practice. So what do we do? So just before I continue, in terms of operators, so basically you solve, the right-hand side is called T mu here, and just the same notation as in the case of discounted cost problems. So what we want to do is we want to model these steps first in an approximate manner, and then connect it later to RL. So these steps are actually implemented approximately, and I want to do it in 2 steps. First, I want to define something called approximate policy iteration for average reward problems, just like we have approximate policy iteration for discounted reward problems, and then relate reinforcement learning to approximate policy optimization. So what is approximate policy iteration for the average reward case? It's exactly the same as in the case of the discounted case. So instead of finding the relative value function associated with the fixed policy exactly, you try to find an approximation to it. And instead of doing exact policy improvement, you do it approximate. So as I mentioned again, as I mentioned before, I just want to recall that the first, so Chen and Magaluri showed in the discounted cost case, not in the average cost case. In the discounted cost case, they showed that these 2 steps can be reinforcement learning algorithms can be interpreted in terms of these 2 steps. For those of you who know reinforcement learning, in the first step, what we are doing is that for a fixed policy, instead of trying to find the true value function or relative value function, you use something called function approximation. So this error is the error that you get from function approximation. And step 2 can be used to model many different schemes for approximate policy improvement. So for example, you might have heard of natural policy gradient, or various other algorithms can be thought of as approximate implementations of this. So our main result is the following. So in the limit as k goes to infinity, if you do approximate policy iteration, the difference between the optimal value, reward, and the reward that you get from the approximate value iteration algorithm that I mentioned is upper bounded by this, where gamma is a constant greater than 0 under some assumptions, and that I will explain what this parameter gamma is. And the main important thing is, now if you let epsilon and delta go to 0, the right-hand side goes to 0, whereas before you had to first let alpha go to 1 to get the average reward, to make the connection to average reward. And then when you do that, it immediately blows up to infinity, and after that, letting epsilon go to 0 or delta go to 0 doesn't matter. Whereas in the discounted cost case, you have 1 over 1 minus alpha square, and then if you let epsilon go to 0, delta go to 0, you get a reasonable result. Whereas that result could not be directly extended to average reward problems. And so our main contribution is to show that there is actually a bound that goes to 0 when epsilon goes to 0 and delta goes to 0. And in the next few slides, I'll try to provide some high-level intuition for this result. And we want to acknowledge the work of van der Waal. There's this beautiful, I guess it's almost a book by van der Waal, which maybe came out of his thesis, where he studied a different algorithm called modified policy iteration, which is not approximate policy iteration. And we use many of the techniques from van der Waal's paper to prove our result for approximate policy iteration. And then we made additional contributions by connecting it to reinforcement learning. Okay, so to give you some intuition, the proof is quite complicated, so I'm not even going to go near the proof, but I'm just going to give you some intuition. And the intuition goes back to ideas that those of you who have done a course on MDP would probably recognize. But I won't have the time to go beyond that. But for those of you who are not familiar with it, I just want to give you an idea of what the difficulties are and how we overcome it, or sort of how we overcome it. So if you look at the for a fixed policy mu, if you look at the fixed point equation to compute the value function associated with the policy, it is of the form T mu v plus R mu is equal to R mu plus alpha times P mu v. Okay. Now, if I subtract T mu v and T mu v tilde from T mu v, then the right hand side is alpha times P mu times v minus v tilde, which from this equation, it is very easy to show that the infinity norm on the left-hand side is less than or equal to alpha times the infinity norm of v minus v tilde. Now, if alpha is less than 1, we have a contraction mapping, whereas average reward corresponds to alpha going to 1. So this is the problem in directly applying the Bird-Cyclist result that I mentioned before, because they fundamentally use the fact that T is a contraction mapping in the infinity norm. So in the limit as alpha goes to 0, we do not have a contraction mapping anymore. And that's where the 1 over 1 minus alpha squared comes in and then messes us up. Okay. So what do we do? So what is another source of contraction? So in the case of average reward problems, people use something called span contraction. Again, experts here would know that. And for people who are not that familiar with it, I just want to go over what span contraction is. So if you take a vector, let's say a vector 8, 4, here's a simple 2-dimensional vector. The span of this vector is said to be the difference between the largest and the smallest values. So the span of this vector is mu. Now, if you take a probability transition matrix and multiply, so this probability transition matrix and multiply by this vector, then the new vector you get is 5 and 6. As you can see, the difference between the largest and the smallest element here is 1. So the span decreases. The span actually contracts. So when you take a probability transition matrix and multiply it by the vector, then the span often contracts. It doesn't always contract, but often it contracts. So when does it contract? It turns out that the span of PV is strictly less than the span of V. In fact, span of PV is less than or equal to 1 minus gamma times the span of V, where gamma is the smallest entry in your probability transition matrix. Okay. So if the smallest entry is greater than 0, which means all the elements of the probability transition matrix have to be greater than 0. So under this condition, the span contracts. Okay. But in general, we all know that a given probability transition matrix may not have all the elements greater than 0. So a natural assumption that sometimes people use to study average cost problems is the most general assumption is something called unichain assumption. And there's even more relaxed assumptions than that. But unichain is a very common assumption. But sometimes instead of unichain, people make something called make an irreducibility assumption. But irreducibility is clearly not enough to guarantee gamma greater than 0, because this is an irreducible Markov chain. You can go from any state to any state, but you cannot directly jump from 1 to 3 or from 3 to 1. So there are certain elements of this probability transition matrix that are going to be 0. On the other hand, if you take this, if you look at 2-step transitions in this Markov chain, then the 2-step transitions will satisfy this property. So it turns out that what we need to make our result go through is that you should look at n-step transitions. Okay, so if there is an n such that the n-step transition probability is such that all the elements are greater than 0, irrespective of the policies you use. So here, notice that the probability transition matrices that I'm multiplying are not the probability transition matrices associated with a fixed policy, but rather with a change with any policy. So over n steps, if I can find an n such that if I use any set of policies over n steps, and the product of the probability transition matrices is greater than 0, then we can ensure that this gamma is greater than 0. Then our result here would make sense. Okay, so then we can get rid of the 1 over 1 minus alpha square, and gamma will be greater than 0. Now, so we need two things. So therefore, we need this along with irreducibility. So we need two things. We need irreducibility under each policy, and we need to make sure that there is a non-zero probability of staying in each state under each policy. So both of these requirements may not hold for some practical MDPs. So what do we do? So let's take a data center example. This is a very simple example. So let's say you have a data center that has two types of jobs. One type of job takes 1 unit of CPU. Another type of job takes 2 units of the CPU. And then our goal is to figure out when a job arrives, which server or servers to allocate the job to. And if the traffic statistics are known, if you have some average reward criterion, you can solve the problem using MDP theory or using approximate by using some approximation to exact policy iteration and so on. But otherwise, one has to learn the information from traffic traces. So there is an algorithm by Mohammed Alizadeh at MIT called Decima, where they looked at Facebook traces, I think, and then they designed an algorithm for a very complicated type of jobs and found the optimal or near optimal solution using reinforcement learning. But in this very simple example, let's say we start off with we don't know what the optimal policy is. Let's say we start off with a policy which accepts jobs of type 2 only if the number of servers occupied is less than. Now, suppose we want to improve this policy using policy improvement. We can't do this in a reinforcement learning setup because we'll never reach, for example, the state 040 because we are never going to allow that many jobs of type 2 in the system. On the other hand, if you use a randomized policy, then you will visit all states with non-zero probability. So what you should do in this case is that there are many things you could do. One simple idea would be with probability epsilon, you just accept or reject a call with equal probability. And with probability 1 minus epsilon, you try to find the optimal policy. So this would be an example of an MDP where it is not truly each policy does not render the system irreducible, but RL requirements, the necessity for exploration and reinforcement learning may naturally enforce irreducibility at the cost of a small performance loss. So you might, with some probability epsilon, you have to accept every call, accept or reject with equal probability. So you might lose some performance, but you can enforce irreducibility with a small loss in performance. So the next question is, I also said that you also have to make sure that the system stays in the same state with non-zero probability. And this problem was solved a long time ago by somebody named Schweitzer. It's called the Schweitzer transformation. And what Schweitzer did was he showed that if you take an MDP and then you say with probability kappa, you stay in the same state. And with probability 1 minus kappa, you use whatever the MDP tells you. And then you also take the reward and multiply by the same 1 minus kappa. This transformation ensures that there is a non-zero probability of staying in the same state under all policies, but it turns out that the optimal policy is unaffected. So this can be shown. So I'm not going to show it here. It's very easy. If you just stick in this transformation in the average reward optimality equation, you will see that the optimal policy will not change. The only thing you will do is that the average optimal reward will be multiplied by 1 minus kappa, but nothing else would change. So the key idea is that, so what you have to do is that you have to allow some amount of exploration, which is anyway needed for reinforcement learning, and then use the Schweitzer transformation. And there are ways to, I mean, here I'm telling you that you would have to multiply, you'd have to stay in the same state with probability kappa and 1 minus kappa with probability 1 minus kappa. You use whatever the MDP tells you. So I'm telling this to you as though I know the probability transition matrix. But even if you don't know the probability transition matrix and you're doing reinforcement learning, then you can just look at a trace that you obtain from applying a policy and slightly modify it to satisfy this condition. And it's something that all of you can figure out by yourself. So I'm not going to talk about it. So basically, the key idea is to allow some exploration and use the Schweitzer transformation to satisfy the assumptions. And then approximate policy iteration can be shown to work in the following sense, that if delta and epsilon go to 0, we can show that, or if delta and epsilon is small, then you get a small error in implementing approximate policy iteration. So even though I mentioned the span contraction property and introduced gamma and so on, our proof does not directly use the span contraction property. The proof is much more involved than that. But nevertheless, that is sort of the simplest intuition I can give you. The real proof involves a somewhat more complicated argument, which was motivated by this paper by van der Waal. So to recap, our result is that we both have a finite time performance bound for approximate policy iteration, and an asymptotic result that says that in the limit as k goes to infinity, you get an upper bound on the difference between what you get from approximate policy iteration and the true optimal reward, and it is of this form. Now, I'm not claiming that this upper bound is a great upper bound, because it could still be very loose compared to practice. But I guess the only thing I'm saying is that at least when epsilon and delta go to 0, this bound goes to 0. Unlike the previous bounds, if you try to approximate the previous bounds for average reward by multiplying by 1 minus alpha, and if you let alpha go to 1 first, of course those bounds blow up, and so they are meaningless in the limit as epsilon goes to 0 and delta goes to 0. And so we've sort of bridged this gap between theory and practice by getting a better bound which doesn't blow up in the limit as alpha goes to 1. Okay, so this is sort of the main theoretical result in our paper. I want to make a few remarks and then make a connection to reinforcement learning before I wrap up my talk in the next 10 minutes or so, five minutes or so. In the discounted reward case, the error scales as 1 over 1 minus alpha square. But not only that, Bertzikas and Tsitsiklis also proved that this reward, that their bound is tight in the sense that there exists a unichain MDP under which this bound is tight. So in theory, you can, in theory, you cannot improve this bound. So to get a better bound, we make an additional assumption. We assume that the Markov chain is irreducible. So it's not like we are contradicting the result. We're not saying that we are improving on the result directly, because that bound is tight. You can't improve on it. So there's no contradiction. But to the best of our knowledge, this additionally assuming irreducibility did not facilitate obtaining a bound previously. And so to the best of our knowledge, no bounds existed before our result, even under the irreducibility assumption. And so under the irreducibility assumption and under the Schweitzer transformation, we were able to show that you can get rid of the 1 over 1 minus alpha. So just to be clear, the only assumption we need is irreducibility. The other assumption that you stay in the same state with non-zero probability is not really an assumption, because you can use the Schweitzer transformation to always convert any MDP to that format. So in the remaining few minutes, I'm going to briefly talk about applications to RL. Reinforcement learning consists of approximate policy improvement and approximate policy evaluation, as we've said. And I guess, sorry for changing the notation here, Q is a different type of value function. For those of you who know what the Q function is, this is the Q function. For those of you who are not familiar with it, it's just a minor variation of the value function that I talked about. In reinforcement learning, it's often easier to work with the Q function rather than the value function. So one modification to approximate policy iteration that we need to make it applicable to reinforcement learning is to allow time varying errors at each step. Okay, in reinforcement learning, the errors at each step will not be upper bounded by a constant, but it would be time varying. And in fact, it's useful to think of them as time varying, because that gives you better bounds. And the theory that I've described can be easily adapted to the case of time varying bounds. So now let's take two examples. An example of approximate policy improvement and an example of approximate policy evaluation. So approximate policy improvement and real policy improvement, what you do is that you maximize over A, this Q of SA. Q of SA is the right-hand side of the Bellman equation. So you maximize the actions over Q of SA for each state S. In softmax policy update, what you do is you choose a policy with a certain probability, which is proportional to E raised to the power of beta times Q. So in other words, as beta goes to infinity, you're exactly doing policy iteration. But as I mentioned, for exploration reasons, you may not want to set beta going to infinity. And if so, that's what you would do in. That's one of the things you might do in reinforcement learning. Is there are many algorithms to do policy updates. One way to do it is using the softmax policy. Another thing you could do is, not another thing. So for policy evaluation, people use something called TD learning. In TD learning, you approximate the value function by a feature matrix multiplied by some theta, and you try to learn the theta. And what you can show is that so by doing these two things, you get a certain error, and the error can be characterized. There are analytical expressions for the error that you can characterize, and then stick it in the approximate policy iteration that theorem that we have. And from that, you get a theorem for reinforcement learning. So for example, I'm just illustrating how our results on approximate policy iteration can be used for reinforcement learning. But basically, in one step, you're doing approximate policy evaluation, and another step, you're doing approximate policy improvement. And most reinforcement learning algorithms can be thought of as consisting of these two steps. And then you can stick it in, and you get a bound like this. As beta goes to infinity, you get exact policy iteration. But then in reinforcement learning, that will not work, because if you let beta go to infinity, you will get a large error here, because you may not be exploring all the states enough. And so your TD learning part of the algorithm will not work very well. And our bound essentially says that. So basically, if you make beta large, you'll make this part of the error small, but then the error due to TD learning may go up. And so you have to choose beta judiciously to trade off between these two. So I think my talk is about 50 minutes long, so I'll conclude it now. So for many practical problems of interest, in particular in the context of communications and communication networks, average reward formulation is meaningful. One example is scheduling complicated directed acyclic graph structured workloads in data centers, and other examples are in wireless contexts. In practice, this is accomplished by choosing a discount factor close to 1, but theoretical guarantees or previous theoretical guarantees are not meaningful in this limit. So we have obtained the first performance bounds, which makes sense in the limit as alpha goes to 1. There is also work that Yashashwini and Mehrdad have done, and I have done in the context of DP and RL for robust versions of average reward MDPs, and actually even earlier for policy gradient algorithms, along with Argadeep, and Argadeep was at UIUC. So all of these papers can be found on arXiv, and I'll conclude my talk now. Thank you.
So thank you, Srikant, for this insightful talk. So it's time for questions now. Any questions from the audience?
Yeah. Hello, Srikant, this is Pamela Kumar. And hi. I was probably at Bell Labs a little bit before you were there. And I was working on it. It kind of reminded me of the basic algorithms we were implementing in pipeline processors. So pipelining had just come, so when we were doing prefetching of algorithms, we were running these traces. We were getting these trace data from the exchange, the telephone exchange, and trying to map it to the branch prediction algorithms and all, as we were designing the architecture of pipeline processors. So now you're talking about a big data center, and it's kind of applying the same thing. So this is an interesting problem that as you're the jobs are coming into the data center and you're allocating the resources, especially in the cloud computing context. I think it's a very important problem. And you may end up in a situation where you may run out of resources or, by doing the kind of allocations. So have you actually used any trace data or something to validate these different algorithms and in what scenario? Because it could be dependent on the application environment as well, right? I mean, a cloud data center, an edge data center versus uh, you know, back office kind of a data center. Have you, do you have some such insights on
I
how
have
to?
not. I have not. Yeah, I have not done it. But I think there is a lot of work in the practical networking community. So in the in SIGCOM, for example, many people have looked at traffic traces and designed algorithms. As I mentioned, one algorithm, one well-known algorithm is called Decima, which Mohammed Alizadeh at MIT designed. And recently, I was talking to some people at NVIDIA who've also designed congestion control algorithms using reinforcement learning. Of course, in Argadeep's thesis, he looked at wireless networks. Also, my former student, Srinivas Chakotai, has done, and Dilip Kalatil together at Texas A&M, have designed a whole bunch of algorithms based on traffic traces. So I guess one question that I am unclear about is when you use traffic traces to design algorithms, what is unclear to me is that what if the real traffic that you see has different statistics than the traffic trace on which you designed the algorithm for? So there's some amount of robustness looks like it needs to be embedded in these algorithms. And Pradeep, Yashashwini, Mehrdad, and I looked at this problem for a while. We did come up with some algorithm, but the algorithm seems to be somewhat complicated to implement. So one thing that would be an interesting topic for future research would be how to robustify these algorithms without making algorithm computationally or not just computationally. There are all kinds of implementation issues with implementing robust algorithms, and whether how to study them is a very interesting future topic of research. So the quick answer to your question is yes, a lot of other people have studied it and studied it successfully, designing algorithms from traces. But I think there are some interesting open questions about how to robustify them.
See, what I've, just dwelling over the word of reinforcement learning. What I feel is if what you're trying to do differently from what we used to do, we would have a static algorithm and build it into the hardware, right? Whereas you are trying to adapt your algorithm. So you could be, adapting by learning the nature of the traffic. You could be having different ways in which your algorithm works, right? Is that a correct assumption? And how do you actually see that happening? Will there be a set of options of algorithms that you switch to use based on the learning that you're doing? How does this adaptation really work?
It is mostly offline. It's not really adaptation. So the main difference is that I think many of the I also worked in Bell Labs before all of these were popular. So I worked there from 91 to 95. And I think most of the resource allocation algorithms that we used, even from traffic traces, it was relatively, the complexity of the system was relatively small. I, when I worked on a project with AT&T about 4 years ago, so we used machine learning for this one problem where basically you're getting all kinds of messages from the network and you have to figure out what is wrong in the network. Why is it generating? Why is the network generating error messages? I worked on exactly the same problem in between around 1993 when I was in Bell Labs. And in those days, the data networks that AT&T used to implement would generate a few hundred messages over a month, actually. Whereas the message log that AT&T provided us for this project had 90 million messages over a 2-week period. So this is, I think, it's a scale that has changed. And so the number of possible states in the network is so large. And as I mentioned, the Shannon number for chess is like 10 power 120, even though we are not playing chess in most engineering problems. It's just that the scale of the problem is large. So all kinds of approximations have to be done. And I think that is where reinforcement learning turns out to be useful. Adaptation is a different, interesting question. So most of the work that I see that's practical in the reinforcement learning context is in the context of offline training. So in the context of online training and adaptation, how to do this is still an interesting open question. And I'm not, people have done it. People have used Q-learning and other techniques online, but not for very large problems. And that's an interesting open question still.
Any other questions? So I have one couple of questions. So am I audible, Srikant?
Yeah.
So the first question is in the proof in the proposed algorithm, proposed methodology, you have talked about the span norm. In the span norm, there was an assumption that the smallest element has to be greater than or equal to 0 for this to work, right?
Strictly greater than 0, yes.
Yeah. So that's why we cannot apply it, but I mean, because we cannot guarantee that the smallest element has to be greater than or equal to 0. But if we look at, let's say, the number of like steps after which we can suddenly go to a particular state and construct a Markov chain considering appending all these states together, then this can be guaranteed, right? And the state space will be large. But
that is enough, actually. You don't need it to be, you don't need the probability transition matrix to have all non-zero elements, just that after several transitions, if it is greater than 0, then that is sufficient.
The second question is,
yes. Was that your question?
Yes, I was, this was not clear to me whether it is at each step you need non-zero or you need it across the, I mean, you can reach any state in n steps, that should be fine.
Yeah, so any state to any state is fine. So let me, so the condition that we require is this, that over n transitions, there exists an n such that over n transitions, you will be able to go from any state to any state. We don't really require you to go from any state to any state in one transition. As long as you're able to go do it in n transitions, that's sufficient. Yes.
And the second question is, like, if we enforce this randomization, like, if you work with randomized policy, then does it impact the bound? This, for example, maybe the optimal policy is a pure threshold policy without any randomization. But if we include this randomization, will it impact the bound?
No, it doesn't. Asymptotically, it will get closer and closer. So you will never, I mean, in the limit is, so that is the sort of the trade-off here. I mean, let me see if I can. It does and it doesn't. So let me try to explain what I mean by that. I mean, in principle, if you're the bound is of this form, so in principle, as k goes to infinity, you will get the correct answer modulo the error in policy evaluation and policy improvement. But if you actually apply this to an RL algorithm, there is a trade-off. So you have to let beta go to infinity for you to be able to get the threshold policy, like you mentioned, right? But if you do that, then your exploration will stop, and so therefore your TD learning will not work very well, and so this part of the bound will go up. So in practice, there is a trade-off. So you're right. I mean, there is an impact. So if it's a small enough problem, then one can use something like policy gradient and converge exactly. But if it's a very large problem, yes, there is always a trade-off, and you won't get the optimal policy. There's a trade-off with having to explore, while at the same time, having the optimal policy will not be a randomized policy. in some cases. And so there is a trade-off. That's exactly what happens in reinforcement learning. So there is an error due to policy improvement, and there's an error due to policy evaluation, and there might be a tension between the two. You're exactly right.
Thank you. So any other questions from the audience? Okay, if not, then let's thank Professor Srikant again for this wonderful talk.
Thank you, everybody. It's a pleasure to be here, and thank you for inviting me. Bye.
Okay, so we'll close the session now. Thank Jaswini and Professor Vazai for joining. Thank you.